Okay, let's unpack this. If you're building anything significant on the cloud these days, especially with microservices, there's this architectural pattern you really can't ignore. The API gateway. We're going to dive into what's really a foundational piece, almost like this sophisticated front door for your systems.
Yeah.
It's pretty much indispensable for, secure, scalable, manageable distributed setups.
Absolutely. And it's indispensable because it tackles a fundamental problem you get when you break services apart, exposing them directly. If your clients, like your mobile app or web front end, have to talk directly to, say, 100 different microservices, well, you're basically asking for trouble in 3 key ways.
Okay, first one being complexity, I imagine.
Skyrocketing client complexity, yeah. The client suddenly needs to know every single service's address, maybe different API versions, different ways to authenticate for each one it needs. That creates really tight coupling, makes the client code fragile, and the whole system becomes incredibly brittle.
And then there's the operational side. Security must be a huge headache.
It's security fragmentation. Suddenly, every single one of those little services that faces the outside world needs to figure out its own rate limiting, its own logging, its own authorization checks. It's inconsistent. You're duplicating effort everywhere. And honestly, it's just a security risk waiting to happen.
And the third one, the one the user probably feels most directly, is latency.
Oh, yeah, the compounding effect of latency is massive. Think about loading something like a product page. Your browser might need info from the product service, inventory, reviews, maybe pricing. That could easily be 4, 5, even more separate network round trips just for one logical action. That cumulative delay, it just crushes the user experience.
So the gateway steps in as this central control point. It's like this powerful policy engine sitting right at the edge, hiding all that back-end complexity. But that brings us straight to a really key trade-off, doesn't it? We need to talk about that up front.
Yes, definitely. The trade-off is unavoidable, really. You are adding another network hop, right? So there's inherently a tiny bit more latency for any given request. However, the architectural thinking here is that this is a very deliberate, worthwhile trade-off. You accept those few extra milliseconds, potentially, for huge gains across the board in security, in consistency, and, frankly, in how fast your teams can actually build things.
So the bet is that having that central management, that coherence, is way more valuable than shaving off every last microsecond.
Precisely. That's the calculation.
Now, if you're newer to this space, all the terminology can get a bit tangled. People often hear API gateway and think of a reverse proxy. How do we draw a clear line there?
That's a really important distinction to make. An API gateway is fundamentally a type of reverse proxy. It sits in front, takes requests, and sends them somewhere else. But a standard reverse proxy usually just routes based on simple stuff, like the URL path or maybe a header. The gateway is specialized. It's aware of APIs, it operates at the application layer. It doesn't just route, it enforces policy. Think of it as a reverse proxy that went to college, learned about APIs, and now does things like authentication, rate limiting, maybe even caching based on the API call itself.
Okay, that makes sense. And what about a load balancer? That also spreads traffic around.
Right, another common point of confusion. A load balancer's main job is distributing traffic efficiently across a pool of healthy backend servers. It's focused on availability and preventing any one server from getting overloaded, usually operating at a lower network layer like layer 4. The gateway often includes load balancing as one of its features, but its primary focus is higher up the stack. It's about application-level routing, making decisions based on API identity, who the caller is, what version they need, and enforcing those API-specific rules.
And this brings us to a really critical concept in modern systems: north-south versus east-west traffic. Where does the gateway fit?
Yeah, this is fundamental for microservices. The API gateway is almost exclusively concerned with north-south traffic. That's the traffic coming in from the outside world, from external clients like browsers, mobile apps flowing down into your system's edge. It's the main entrance.
So the gateway is the front door. Then what handles the internal chatter, like service-to-service communication?
That's where something like a service mesh comes in. That manages the east-west traffic, the internal kind of sideways communication between the microservices already inside your network boundary. They're complementary tools, really. The gateway handles the edge, simplifies things for external clients, and enforces boundary security. The service mesh handles the complex, secure, and reliable communication once a request is already inside.
Got it. Okay, let's shift gears to the gateway's toolkit. Once it grabs that incoming request, what kind of jobs is it taking off the plate of those back-end service developers?
Well, the absolute first one, the non-negotiable one, is security, specifically centralized authentication and authorization. The gateway is the place where you check API keys, validate JWTs, maybe handle OAuth flows. This is huge because it means your individual microservice teams can stop writing boilerplate security code over and over again. They can just focus on the business logic they're supposed to build.
And it also acts like a traffic cop, right? Protecting the service.
Exactly. That's rate limiting and throttling. This is crucial protection. The gateway controls how many requests a particular client, or maybe all clients hitting a specific API, can make in a certain time window. This protects your backend services from abuse, whether it's a malicious DDoS attack or just, an accidental runaway script hammering your API.
I also find the transformation part really interesting. It feels like the ultimate way to decouple things.
It really is powerful. Request and response transformation lets the gateway act as a mediator between different formats or protocols. Maybe you have old clients that speak SOP, but your new microservice uses REST and JSON. The gateway can translate the incoming SOAP request into REST, send it to the service, get the JSON response, and translate it back to SOAP for the client. It's fantastic for maintaining backward compatibility. You can evolve your backend services without breaking your existing clients immediately.
Okay, now let's talk resilience. This feels like where the gateway moves beyond just managing traffic to actively preventing things from falling apart.
Yeah, and what's really key here is that centralizing this resilience logic stops what you might call scattered resilience. If every single microservice team tries to implement fault tolerance slightly differently, well, the overall system behavior becomes unpredictable. Putting it in the gateway ensures consistency.
And there are two main patterns we lean on here. First one is simple retries, right?
Yeah, automatic retries. Networks are glitchy sometimes. Things fail transiently. So the gateway can be configured to automatically try a failed request again, maybe 2 or 3 times. Crucially, it usually does this with exponential backoff waiting a bit longer between each retry. This stops it from just slamming a service that might be temporarily slow or struggling.
Okay, and then the big one, the pattern everyone talks about, the circuit breaker. How can we make that really click for listeners?
Right, the circuit breaker. Think of it like an electrical circuit breaker in your house, but for API calls. It has 3 main states. Normally, the circuit is closed. Traffic is flowing just fine to the backend service. Everything's good. But let's say the backend service starts consistently failing requests. Maybe errors spike above a certain threshold, like 50% errors in the last minute. The gateway then trips the circuit, moving it to the open state. When it's open, the gateway doesn't even try to send requests to that failing service. It just fails them immediately, maybe returning a cached response or a standard error. This is vital. It stops requests piling up and overwhelming a service that's already down. It gives the service breathing room to recover.
Right. It stops the cascading failure, protects the struggling service and the client from just waiting forever.
Exactly. Then, after a configured timeout period, say, 30 seconds, the circuit moves to the half-open state. In this state, the gateway cautiously lets just a few requests through, like a small test batch. If those succeed, great. The gateway assumes the service is healthy again and causes the circuit returning to the closed state. Normal traffic resumes. But if those test requests fail, it immediately trips back to the open state for another timeout period. It's this self-healing mechanism that prevents one flaky service from bringing down the entire application.
That makes perfect sense. That centralized control over failure is so important for microservices. Okay, let's step back to the architecture level. When teams decide to use a gateway, they face choices about how to deploy it. It seems like a trade-off between flexibility and simplicity.
It really is. And the pattern you choose has big implications for how your teams work. Most organizations, quite reasonably, start with the simplest pattern, the centralized edge gateway.
One big gateway handling everything coming in. Sounds straightforward.
Yeah, it's simple to manage initially. One place for all policies, one stable interface for all your clients. But here's where the organizational friction starts to creep in. As your company grows, maybe from 5 microservices to 50 or 100, that single gateway and the team managing it can become a bottleneck. Every time a product team needs a new route or a policy tweak, they have to file a ticket and wait for the central gateway team. This can really slow down development velocity across the board. And if not scaled properly, it can become a single point of failure.
Which naturally leads organizations to look at more complex patterns, like the 2-tier gateway maybe.
Exactly. That often involves having one gateway layer focused on external security and routing at the very edge, and then maybe another internal gateway layer closer to the services, perhaps handling more fine-grained logic or internal traffic segregation. It definitely increases complexity, but it starts to distribute the load and potentially the ownership.
And then there's the extreme end, the microgateway pattern. This almost sounds like it goes against the original idea of centralizing things.
It kind of does in a way. With microgateways, you might deploy a small, dedicated gateway instance alongside each microservice, or maybe for each small team or domain. This gives maximum autonomy. Teams can manage their own specific policies, their own routing, without waiting on anyone else. But the trade-off is huge operational complexity. Now, instead of managing one or two gateways, you might be managing dozens or hundreds. You lose that centralized control point, so it's this constant tension.
Right.
Maximum delegation and speed versus simplicity and centralized governance.
And dealing with that complexity is precisely why managed services like Azure API Management, APM, have become so popular. But choosing one isn't just about features, right? There's a big cost and scale calculation involved.
Oh, absolutely. When you opt for a PaaS solution like APM, you're essentially paying Microsoft, in this case, to handle all the underlying infrastructure management, the scaling, the patching, keeping the gateway instances themselves highly available. That's a massive operational burden lifted. And APM itself isn't just the gateway component, it's a whole platform. It includes the gateway runtime, yes, but also a management plane for configuration and analytics, and a developer portal for API discovery and documentation.
And we see different tiers like basic versus premium with significantly different price tags and capabilities.
Exactly. The tiers reflect the features and the service level agreement, SLA, you need. For example, APM's Premium V2 tier offers things like a 99.99% availability SLA, integration with private networks, VNet injection, maybe multi-region deployments. These are complex enterprise-grade features. The basic tier might be fine for development or less critical APIs, but it won't have the same resilience guarantees or networking options. So you're paying more for higher reliability than those advanced features that are really hard and expensive to build and operate yourself.
And another point of confusion often comes up, APM versus Azure Application Gateway. People sometimes think they do the same thing.
Yeah, they're definitely distinct but designed to work together. Azure Application Gateway is primarily a Layer 7 load balancer, but its killer feature is the Integrated Web Application Firewall, the WF. Its job is to sit at the very edge, inspect incoming web traffic for common attacks like SQL injection or cross-site scripting, and filter out malicious requests before they even get deeper into your network. APM, on the other hand, is a specialized API governance layer. It handles things after the WAF has cleaned the traffic API-specific authentication, rate limiting, request response transformations, routing to the correct backend service based on API rules.
So a common robust pattern is to use both.
Precisely. You typically have Application Gateway with the WA enabled at the public edge. It routes the cleaned, legitimate HTTP traffic to an instance of APM, which might be deployed privately within your virtual network. Then APM applies all the specific API policies before finally forwarding the request to the actual backend microservice. It's a layered defense approach, letting each service do what it does best.
Makes sense. Okay, so regardless of the pattern or service you choose, monitoring this thing has to be critical. You can't manage what you can't see.
Absolutely non-negotiable. Observability needs to be baked in from day one. You need the classic three pillars: logs, metrics, and traces. For something like APM, Azure Monitor is the central place. It gives you key metrics out of the box: request counts, backend latency, gateway latency, error rates. You absolutely need to set up alerts based on these. If your 5xx error rate suddenly spikes, you need to know immediately, not find out from users.
And what about when things go wrong? Like a specific request fails and you need to figure out exactly why. Maybe a policy misfired or the circuit breaker tripped.
That's where tracing comes in. And APM has a specific feature, often just called the tracer. It lets you capture a detailed step-by-step execution trace for a specific request as it flows through the gateway's policy pipeline. You can see the incoming request, how each policy transformed it or didn't, what the request looked like going to the backend, the response coming back, and precisely where an error might have occurred. It's incredibly useful for debugging complex policy logic.
To really drive home the importance and scale of this, we probably have to mention the classic example, Netflix and Zool.
Yeah, you really can't talk about API gateways at scale without talking about Netflix. They were pioneers in microservices, dealing with, over 1,000 services serving millions of streams globally. They built and open sourced Zool, their API gateway, precisely to manage this complexity and scale.
And what were the really critical jobs Zool was doing for them at that massive scale?
Oh, all the core functions we've discussed, but just amplified. Dynamic routing was huge, figuring out where to send requests across a constantly changing landscape of services. Load balancing, obviously, security enforcement at the edge, but also things like sophisticated request response transformation, maybe tailoring payloads for different devices to save bandwidth, and extensive caching of metadata to improve performance. Zool was the linchpin that allowed them to operate that huge microservices architecture reliably and keep innovating quickly.
It really hammers home that the API gateway isn't just a nice to have, it's fundamental for solving those core challenges of security, resilience, and complexity in distributed systems. So bringing it all together, what's the main takeaway for someone listening, trying to figure out how to approach this?
I think for most organizations, especially if you're starting out or dealing with a moderately complex system, the recommendation is pretty clear. Start with the centralized edge gateway pattern. It gives you the most immediate benefits with the lowest initial complexity. And critically, strongly consider using a managed service like APM or its equivalent on other clouds. The operational effort required to build, scale, secure, and maintain your own gateway platform is immense. Offload that if you possibly can.
That seems like solid advice for getting started.
Hmm.
But as always, we like to leave listeners with something to chew on, a forward-looking challenge.
Right. So while adopting a gateway initially simplifies things, especially for clients, remember that bottleneck issue we talked about with the centralized model. The real strategic challenge, especially as your organization and systems mature, isn't if you should use a gateway, but when does that initial simple centralized gateway become the main obstacle to your teams moving fast? Recognizing that inflection point, the point where the cost of centralized control outweighs its benefits, and figuring out how and when to maybe transition towards a more delegated model like two-tier or even micro gateways without causing chaos. That's the really hard architectural and organizational problem you'll eventually face. Knowing when to decentralize ownership again, that's the tricky part down the road.